Hey everybody, this one is 5M collisions. So the scenario is a wooden cart of mass capital M is set on a horizontal section of track. The cart experiences negligible friction as it rolls. A dart of mass lowercase m, which is less than uppercase m, is fired with initial speed v toward the cart, which is initially at rest. So let's label a few things on here. They say this one is capital M. They say this one is lowercase m. We can see that this one is speed v. And even though they don't say it, it's just going to help me to work through this to be a bit more specific than this little m's less than the big M. I'm going to say that big M is equal to 2 times the mass of the little m there. So we got 3 different cases it says to consider. Case 1, the dart embeds in the cart, so and they roll off together. So that's an inelastic collision, completely inelastic. Case 2, the dart bounces backward off the cart, and bounces back like that. And case 3, the dart passes through the cart, and then keeps moving in that case. So they want us to do some of these motion diagrams for this case here, or each case. So first case, case 1, that's when the dart embeds itself in the cart. So let's do some drawings here. I am going to, and again, I've thought this out, so it makes a bit more straightforward path than maybe you did yourself, but I'm going to say the mass of the little one's 1 wide. And I'm going to say 1, 2, 3, 4, 5, 6. So this, let's say, represents the momentum diagram for the dart coming along. So it is 1 wide and 6 tall, 1 unit of mass, 6 units of velocity. So all together, we have 6 units of momentum. The cart's initial momentum is 0. So it has 2 units of mass, I pretend, but all you need to do is do that it's bigger than this one. And so 2 units of mass, but no velocity, so no momentum. So here's the key. We've got 6 plus 0 is 6, so that means there's gotta be a total of 6 squares over here. 6 units of momentum, that's what the squares really represent. So how can we get there? Well, if they embed the dart in the cart, then they're gonna be stuck together. So our total mass will not be 1 or 2, but 3. So 1, 2, 3 wide there. So how do we get to 6 if we're 3 wide? We have 2 units of velocity like that. So it might help to actually picture that the dart's a kilogram and it was going 6 meters per second, and the cart is 2 kilograms and it was going 0. Then when they join together, we would have 3 by 2, which would get us back to a total of 6 units of momentum there. So that is case 1, where the dart embeds in the cart. Let's do case 2, where the dart bounces backwards off of the cart. So I'm gonna do the dart again. So 1, 2, 3, 4, 5, 6, just like before. So 1 by 6 gives us a total of 6 there. And the cart again, it will have a total momentum of 0. So 2 wide there. So just like before, we've got 6 plus 0 means a total of 6 on this side. So we have to have a total of 6 on this side as well to conserve momentum. So what's this going to look like? It says the dart bounces backwards off of it. So that means we're going to have a negative velocity. How much? They don't say. But again, I've thought this through, that it's going to work out nice with my squares. Let's say we bounce back at 2. So negative 2 and 1. Still a mass of 1, but let's say we bounce backwards at 2 meters per second. And so this will give us a total momentum of negative 2 for the dart. But remember what we got to get up to. We got to get up to a total of 6. So if we're at negative 2 in the hole, but we got to get up to 6, then that means the cart has got to have a total here of 8 to get us to 6 here. So how could we do that? Well, the cart, remember, is 2 units of mass, I'm pretending. And so how could we get to 8? 1, 2, 3, 4 units of velocity upwards like that. So again, what is the situation we just described? A 1 kilogram dart going 6 meters per second hits a 2 kilogram cart going 0 meters per second, and then the dart bounces backwards at -2 meters per second, then the cart here would have to go forward at 4 meters per second there. Let's do the third case. And this is the dart passes through the cart. So in this case, once again, same beginning here. So 1 wide and 1, 2, 3, 4, 5, 6 tall there. So we're 1 by 6 for a total of 6 for the dart. And just like before, the cart here is 2 units of mass, but it's not going any speed at all beforehand, so it has 0 momentum. So 6 plus 0 is a total of 6 before, so we have to have a total of 6 afterwards again. But now it says the dart passes through the cart. So imagine something like this. It's slowed down, but not much. So 1, 2, 3, 4, I'm going to pretend. So no longer 6. We slowed down a bit. We slowed down from 6 to 4. You get that it would slow down as it passed through there. So here we have a momentum of 4. How are we going to get to a total of 6? That means the cart would have to have a momentum of 2 there. So how do we get to a momentum of 2? If we have 2 units wide, then we would only have 1 unit up here, so 2 by 1. So again, what this example that I've made up here is basically saying a 1 kilogram dart, going 6 meters per second, hits a, no cat, I can't play with you right now, I'm making a video. A 2 kilogram cart going 0 meters per second. The dart passes through, but only with 4 meters per second of speed, and that would make the cart go forward with 1 meter per second of speed. So now let's do some quantitative analysis of this. So that means we are going to do it case by case and actually solve for it. So let's do case 1 here. This is when the dart embeds in the cart. So momentum initial is equal to momentum final. The initial momentum is the little m times the initial v. And let's solve for, in each case, the v2f. So that is the velocity of the cart afterwards. Well, in this case, there's a combined mass in case 1. So it would be the little m plus the big M times this v2f, they're calling it. So when we go to solve for v2f, it would be mv divided by their combined mass, like that. So now let's look at case 2. Case 2, if you remember, it was where it bounced backwards. So again, the initial momentum is equal to the final momentum. We've got mv for the dart again. The cart doesn't add any momentum. This time, because it goes backwards, we're going to have some negative momentum of little m times v1f, we could call it, so object 1 backwards, plus the mass of the cart times v2f. So let's start to solve for v2f. We've got to move this to the other side. So mv plus mv1f, and then I'll go ahead and divide by that big M there, and then that will give us v2f. So there we have the final velocity for the cart in case 2. Now let's do it for case 3 here. That's when the dart passes through it. So in that case, once again, the initial momentum is equal to the final momentum. We start off with mv as our initial momentum. This time, the dart is going to go through with some new final velocity forward, so it's positive, and that will be the big M times its v2f. So when I go to solve for this, first thing, I'll subtract this to the other side. So mv minus mv1f, and then I'll divide by that big M. And so there is my final velocity of the cart in that case. So notice sort of the similarities here. These two are exactly the same, except this one is going to be smaller because we're subtracting it, this term, versus adding that term here. And then over here, we don't have that term up top, and we're dividing by a bigger term down here. So now they want to know, then the final part, it says rank the cases in terms of the distance up the incline that the cart travels after its interaction with the dart, and explain your ranking in terms of conservation of momentum and conservation of energy. So if we look there, first of all, where's the cart going to go the furthest up the hill? Well, that's when the cart has the greatest kinetic energy, because that kinetic energy is going to become gravitational potential energy. So a ranking of the kinetic energies for the cart, I'll call that object 2, will give us a ranking of their gravitational potential energies, which will give us a ranking of their heights. Well, what determines their kinetic energies? That's the velocity of the cart, what they're calling V2F, so the velocity of the cart afterwards. So how are we going to rank that? Well, let's look at this. Which one of these is going to be the biggest? This one, because we're adding 2 terms up top, and we're dividing by the smallest amount of mass right there. So case 2 is going to be the furthest up the incline. Then we're down to these 2 here. Then if you look at it, well, now it's clear between these 2. This one compared to that one, we're not only subtracting the term from the numerator, so there's that. So that is what's going to make case 1, but we're also here dividing by a bigger number there. So that sort of makes it a little bit more complicated. But if you work this out, whatever this is going to wind up being a smaller number here than that one. And so case 1 will go here, and case 3 will go right there. What they actually, let me pull up what they have written here. They say the larger the velocity of the cart post-collision, the more kinetic energy the cart will have, meaning the higher the cart will go up the ramp, converting kinetic energy into gravitational potential energy. As shown in both the mathematical representation and the momentum charts, the cart will have the largest post-collision speed in scenario 2 and the smallest post-collision speed in scenario 3. Actually, let me bring those back here so that you can see them. So case 1 here, notice it worked out that the cart would be the same as the dart speed would be 2. In case 2, we worked out that the cart would have a speed of 4. And in case 3, we worked out that the cart would have a speed of 1 there. So 2, and then 1, and then 3 there. So again, this one would have a speed of 4 in our pretend scenario, case 2. Case 1 would have a speed of 2. And case 3 would have a speed of 1. You can think about it too in terms of if the dart bounces backwards, just basically the cart's going to have even more momentum to make up for that negative momentum there. If the dart embeds itself, then that is going to be more velocity than when it passes through, because if it passes through, the dart's still going to keep most of the momentum for itself, so it's not going to be able to give as much to the cart.